Google runs over 2 billion containers per week. That's a massive scale. Here's what most engineers get wrong. They struggle to explain Kubernetes networking beyond basic YAML files. By the end of this video, you'll understand how pods, services, Ingress, and CNI plugins work together to power cloud-native applications at scale, and how to ace related system design interviews. Remember that 2 billion number? We'll see why it matters when we discuss scaling and reliability.
Let's clarify the scope. We need to design a networking solution for a microservices application deployed on Kubernetes. Functional requirements include service discovery, load balancing, and external access. Non-functional requirements are high availability, low latency, and security. Let's assume we're building an e-commerce platform. Key questions to ask up front: what's the expected traffic? What are the latency SLAs? Do we need to support mutual TLS? We're focusing on the networking layer itself, not the application logic. This isolation is crucial for simplifying the problem domain and allowing us to focus on core networking concepts.
Let's estimate our traffic. Assume 10,000 requests per second at peak. If each request is 1 kilobyte, that's 10 megabytes per second of bandwidth. With 100 microservices, each service needs to handle roughly 100 QPS. For storage, etcd stores the cluster state. A small cluster might use 10 gigabytes. However, we need to account for logs and metrics. Let's allocate 100 gigabytes for monitoring data. Bandwidth between pods will be significant, so we need a CNI plugin that provides high throughput. This estimation is crucial for understanding the scale of the system and making informed design decisions later on. Remember this estimation. It will be useful when we discuss scaling strategies.
With the foundation in place, let's tackle the high-level design. Pod networking is the base. Each pod gets its own IP address within the cluster. CNI plugins like Calico or Cilium manage this, using techniques like creating virtual Ethernet pairs, VETH, and network namespaces. Services provide stable endpoints for pods. We'll use cluster IP for internal communication, node port for exposing services on each node's IP, and load balancer for external access. Ingress controllers manage external access using Ingress resources. These define routing rules. The data flow is as follows. External requests hit the Ingress controller, which routes them to the appropriate service. The service then load balances traffic across the pods. Pods communicate directly with each other using their IP addresses. We use CNI plugins because they provide a standard interface for configuring pod networking, allowing us to switch between implementations without modifying application code. Alternatives like manually configuring network namespaces are complex and error-prone. This design enables service discovery and load balancing, which are essential for a microservices architecture.
Now that we understand the high-level design, let's dive deeper. Kube-proxy is a critical component. It implements service routing using IP tables or IPVS. IPVS provides better performance at scale because it uses a hash table lookup instead of iterating through rules. DNS resolution within Kubernetes is handled by kubedns or core DNS. Pods use DNS to discover services. The algorithm kube-proxy uses to route traffic is essentially a distributed hash table. A common candidate mistake is not understanding the difference between Ingress resource and Ingress controller. The controller implements the resource. Your interviewer will push back. Why not use a service mesh like Istio? Service meshes provide more advanced features like traffic management and security, but they add complexity and latency overhead. For a simple e-commerce platform, Ingress is sufficient because it's simpler to configure and manage. We gain simplicity but sacrifice advanced features. The trade-off is complexity versus functionality. Stop. Think about this. What happens if kube-proxy fails? Kubernetes will automatically restart it, but during that time, service routing will be disrupted. This is where monitoring and alerting become crucial. A common mistake is to not have proper alerting in place.
This brings us to a crucial challenge: network policies. Network policies isolate pods and control traffic flow, acting as a firewall within the cluster. We can define rules to allow or deny traffic based on labels. This is crucial for security and preventing lateral movement of attackers. The database choice for storing network policies is etcd because it's the central store for Kubernetes cluster state and provides strong consistency. The schema includes fields like pod selector, ingress rules, and egress rules. We need to index the pod selector for efficient lookups. Pause and think, what's missing from this schema? We need audit fields like created at and updated at for tracking changes. The trade-off is security versus complexity. More granular policies require more configuration.
Having locked down the data model, let's discuss scaling and performance.
Caching is crucial for reducing latency and improving performance. We can cache DNS lookups and API responses. We use a cache-aside pattern with Redis because it allows us to scale the cache independently of the application and provides low-latency access. Replication ensures high availability. Sharding can be used to distribute the load across multiple clusters. A CDN can cache static content. The biggest bottleneck is often DNS resolution. To handle 10,000 QPS, we need a highly scalable DNS solution. Your interviewer will push back. Why not use a service mesh for caching? Service meshes can provide caching, but they add overhead and complexity. Redis is a simpler and more efficient solution for basic caching. The key insight is to use the right tool for the job. Remember those 2 billion containers we mentioned at the start? This is where that scale matters. Without caching, DNS resolution would become a major bottleneck, preventing us from handling that level of traffic and potentially causing cascading failures.
The next piece of the puzzle is reliability and operations. Fault tolerance is critical. We need to ensure that the system can handle failures. We use multiple replicas for each pod to ensure high availability. Monitoring is crucial for detecting issues. We use Prometheus and Grafana for monitoring because they provide comprehensive metrics and visualization capabilities. Alerting is used to notify operators of critical issues. We can set up alerts for high latency or error rates. We need to monitor the CNI plugin to ensure that it's functioning correctly. If a node fails, Kubernetes will automatically reschedule the pods on another node. The key is to have a robust monitoring and alerting system to maintain the 2 billion container scale. We've covered a lot of ground. The key trade-offs are complexity versus functionality, security versus performance, and cost versus scalability. The biggest bottleneck is often DNS resolution, especially at the scale of 2 billion containers. Next steps include implementing mutual TLS and exploring service meshes. Remember, Kubernetes networking is a complex topic, but understanding the fundamentals is crucial for building scalable and reliable cloud-native applications. Now you're ready to tackle those system design interviews.
If you found this helpful, please like, share, and subscribe for more system design deep dives like this.